Okay, so today we are going to talk about chirality, and before we really go ahead and learn what chirality is, we are going to hear a story. This is a story of a chemist named Frances Kessley. She was a chemist in FDA in the United States of America, and a drug was launched in around 1950s to 1960s in the European market by the name of thalidomide. The drug was used to reduce morning sickness or nausea in the pregnant women and was being popular in the European countries as well as Canada. And the drug company also wanted to sell the drug in the US, and they were trying to pressurize Frances Kessley to give the FDA approval. So, they were trying to get her to approve that the drug was safe for pregnant women. However, despite of all the pressure, she refused to accept that the drug was safe, and she kept denying their requests, saying that more information was needed to claim the drug to be safe. And very soon she was proven right. Reports soon started coming in from Europe and Canada of babies being born with lots of birth defects and without limbs, some of them missed some body parts. And turns out the thalidomide that the mothers took during their pregnancy was responsible for causing these birth defects in more than 10,000 babies. So, what really happened? How can the drug molecule turn out to be kind of a poison for these babies? Turns out that thalidomide exists as two different molecules which are two different enantiomers. So, we will look at what enantiomers are, but before that, if you look at this molecule closely here, if you look at this particular carbon, now that carbon has four different attachments. It has a hydrogen, it has a nitrogen attached to it, and if you look at on these two sides of the ring, have different attachments to it. So, you can imagine that this particular carbon can form these four bonds such that they can be arranged differently in three-dimensional space. So, you can imagine that in one case you have the nitrogen coming towards you, which is what we have drawn, or you can also draw it such that the nitrogen can go away from you. So, this is what the two molecules really can look like. In fact, these two molecules are called as enantiomers of each other, because if you really see, both of them are mirror images of each other and they are non-superimposable mirror image. So, here I have drawn the R thalidomide which has the mirror image of S thalidomide. Now, what happens is that the drug binds to receptors in our body. Whenever we take a drug, our body is going to have some receptors that bind to it. As you can imagine, one of the molecule binds to the receptor. So, for example, the R thalidomide will bind to the receptors, whereas the S will not bind. And what was happening is that the S thalidomide was actually targeting some other receptors in the body, resulting in the birth defects that were happening in babies. So, when doctors prescribed thalidomide, they were not aware that thalidomide was existing as a mixture of two compounds that resulted into two different results. As you can see, the R was the right drug and S was the poison for the babies. Frances Kessley won the President's Award for stopping the sale of thalidomide in the US. So, for her sheer determination of not approving or not succumbing to the pressure that was put by the drug companies, she actually won the President's Award, and her work was applauded worldwide. So, as you can see in this particular figure, you can see that I have a pair of enantiomers which are mirror images of each other. As you can see, this is the chiral carbon in each case. They are mirror images, they have four different attachments, and if I look at a binding site of a receptor, you can see that as I try to fit one such that all of them match, I cannot do the same thing for the other. If you can see, in these two cases there is no matching, right. So, as you can imagine, enantiomers cannot bind to the same drug receptors if the receptor itself has chirality, or the receptor itself has some asymmetry that requires a particular enantiomer to bind to it. This incidence caused a global awareness on the properties of molecules called as chirality. So, now let us look at what is chirality. So, here I have a molecule here, it is alanine, in fact it is one of the amino acids. Now, if you notice here we have a chiral carbon, okay, and if you see that carbon has 4 different attachments. The dash is something that we say goes away from us and the wedge comes towards you. So, in this case the NH2 groups are coming towards me and the hydrogens are going away. One of the things I want to point out about these chiral carbons, sometimes you will also see them referred to as stereocenters. Now, something about these stereocenters, remember a carbon, a tetrahedral carbon is a stereocenter if it has 4 different attachments to it. So, here I have, for example, this is one of the chiral centers and it has 4 different attachments, a blue, green, red and a white sphere. If I look at its mirror image, which is, let me just create a mirror image, this is the mirror image, right. If I want these 2 molecules to superimpose on each other, there is no way I can do that. So, anytime I try to combine such that 2 of the colors overlap, so let us now overlap the white and the green. So, these 2 are overlapping, but as you can see, as I overlap the white and the green, the blue and the reds do not match. On the other hand, if I try to really overlap the blue or the red, the white and the green will not match. So, there is no way for, if I have a chiral center or a pair of enantiomers really, I cannot superimpose them such that they directly superimpose on top of each other such that all 4 groups match with each other. One of the things I want to point out is that if you have less than 4 different attachments. So, here for example, in this molecule I have the central red carbon has 3 different attachments. So, you have a blue, a black and 2 of the white spheres. So, this particular carbon is not a chiral carbon because it has 3 different attachments, and if I look at its mirror image, so this is a mirror image or its enantiomer as if you want to call it, but I can easily superimpose them such that all the colors kind of coincide with each other. So, you can see that the blue and the black match as well as the 2 whites match. So, if I want to have a pair of enantiomers, they should be non-superimposable and they should be mirror images of each other such that you cannot lift one of these mirror image, put it on the other and cause a perfect superimposition. So, now let us look at what are these chiral carbons or what are the chiral centers. So, as I said, sometimes we also call them as stereocenters. So, one of the ways for a molecule to be chiral is to have a stereocenter. A stereocenter is an atom or a group of atoms sometimes that can potentially cause a molecule to be chiral. Now, stereocenters can give rise to chirality. So, please remember what I am saying here, I am saying they can give rise to chirality. They are not only condition that is necessary to give rise to chirality, and in fact, in the next class we are going to look at some of the examples wherein there is a stereocenter but the molecule is not chiral, or a molecule is chiral but does not have really a tetrahedral carbon. So, stereocenters can give rise to chirality. We just looked at enantiomers, and enantiomers are a pair of stereoisomers. So, I also want to talk about one more term here. We looked at constitutional isomers which were of the same molecule, that they have the same molecular formula but different structural formula. Then we also looked at conformational isomers which can be interconverted into each other through a rotation of single bond. Now, here we are looking at one more set of isomers, these are stereoisomers, and stereoisomers cannot be interconverted into each other through a set of rotations. So, for example, here I have a pair of enantiomers, right, the same pair that we looked at, and I cannot interconvert this to this through a simple bond rotation. If I really have to interconvert this into this, what I will have to do is I will have to break a bond and reattach a bond to in order to go from one of the enantiomers to the other. So, you cannot interconvert enantiomers just like that from one to another, you will have to break and make a new bond. So, stereoisomers are the same constitutional isomers, but they differ in the way they are arranged in a 3D space. So, their molecular formula, molecular weight is exactly the same, but they differ in the way they are arranged in the 3D space around the atom. So, as we said, having a stereocenter does not make a molecule chiral. Chirality also needs lack of symmetry. As you can imagine, a symmetric object has a plane of symmetry in it. So, for example, here I have a pair of spectacles and they do have a plane of symmetry such that one part of the object matches with the other part of the object, right, such that this particular object itself is symmetrical, or for that matter this water bottle is symmetrical such that you can have a plane of symmetry that goes through the water bottle, and in fact the object is symmetrical. You will see that it is not a chiral object. On the other hand, if I look at my keys here, right, as you can see this particular key does not have a plane of symmetry. I cannot create a plane such that the two parts exactly match with each other. So, it is possible for this particular key to have an enantiomer, okay, which is its mirror image and which is non-superimposable. If you look around, you will find many objects that are non-superimposable mirror images. One of them are your pair of hands. So, my two hands are non-superimposable mirror images of each other. So, I have to lift one place and then put it on this. As you can see, I cannot create a superimposition, perfect superimposition for my two hands. So, as we saw that symmetric objects have a plane of symmetry and they can be superimposed onto each other. In fact, if you remember this molecule, it has a plane of symmetry, right. If you draw a line here, you can see that this half of the molecule is the same as the other half of the molecule. So, they can be easily superimposed, right. So, the molecules that have a plane of symmetry can be easily superimposed, whereas the ones that do not have the plane of symmetry, it is very difficult to create the superimposition. And this property of asymmetric objects to give rise to the fact that they cannot be superimposed really gives rise to chirality. Okay. So, now let us look at how to name these molecules, because if we have two separate set of molecules, we need to be able to identify them and we need to be able to name them. So, now we are going to look at the Kahn and Gold and Prelog's rules in order to name enantiomers. So, let us start with our alanine. So, this is one of the molecules, right, and I want to now name it. Now, the rules go like this. The first rule is that we first locate the chiral carbon. So, in this case it is very easy. This is the chiral center. You will see that many a times it is represented with an asterisk. So, herein you can see that the asymmetric center is attached to a nitrogen, a carbon and a hydrogen. After this, what we are going to do is we are going to number them such that we are going to number them based on the atomic number. So, the highest atomic number gets the first priority and the lowest atomic number gets the last priority. So, we are going to number them. So, we are going to rather rank them, not number them. So, rank them according to their atomic number, right. So, in this case, for example, nitrogen has the atomic number 7. So, that will be the first priority. Now, I have two carbons, right, and in any case both the carbons have the same atomic number. So, I cannot differentiate. So, what I do next is I look at the next attachment. So, for example, this carbon here is attached to an oxygen and a hydrogen, right. So, this particular carbon has a double bond to one of the oxygens and a single bond to other oxygen, whereas this other carbon here has just a attachment to 3 other hydrogens. So, then this particular carbon gets the second priority and then the other carbon, the methyl carbon, gets the third priority. Hydrogen, as you can imagine, will get the fourth priority. Now, once you have ranked all the attachments to a chiral carbon, what you are going to do is we are going to arrange these or look at the molecule such that the least priority group goes away. Okay. So, this is one of the key steps. So, the least priority group should go away from you. As you can see, the dashed representation means the hydrogen is already going away from you, and then what we do is we look at how the other 3 groups are going. So, for example, in this case, if this is the hydrogen, I make it go away from you, and then you look at how these priorities are, either are they clockwise or they are counterclockwise. If they are clockwise, if they go clockwise, then in fact you are going to have to call them R, which stands for rectus, and if they are counterclockwise, then they will be called as S for sinister. Now, one quick way, let us figure out whether first of all this alanine is R or S. As you can imagine, in this case we have labeled our priorities. So, this is moving in this particular fashion. So, this is going clockwise. So, this is R. Okay. If I look at its mirror image, so let me draw its mirror image here. So, again 1, 2, 3. If I look at the mirror image, then it goes in the opposite direction, right. So, it rotates in the opposite direction, and that will be the S stereoisomer. Okay. One good quick way to remember what is R and what is S, sometimes people tend to forget what is clockwise and counterclockwise. So, here is a quick way to remember. When I write R, my hand moves in the clockwise direction first, and when I write S, my hand moves in the anti-clockwise direction first. So, this is a very quick way to remember what is R and what is S. Okay. So, I am also going to show 1 or 2 more tricks to really identify whether a stereo center is R or S. So, let us go forward and let us look at some of the tricks. The next example I want to solve here is this particular molecule, which is carbone. Now, they have already solved it, but let me go over the example again. Now, carbone is actually a natural product, okay, and carbone is found in spearmint oil, and it is also found, its enantiomer for that matter, is found in the caraway seed oil. So, now let us try to solve whether this is really R or S. Let us try to verify. Now, in this case, remember, they do not draw the hydrogen. So, in this case we do have a hydrogen that is going away from us, and the carbon is coming towards you. So, now let us try to arrange them on the basis of priority. If I really look, this carbon is attached to 3 carbons and a hydrogen, right. Let us also draw the attachments to these carbons, so that we can make it very evident here. Now, in between these 3 carbons, which one should really get a higher priority? And for that, what I am going to do is I am going to draw the molecule again. So, now let us try to rank the attachments to this particular carbon. As you can see, you have 3 carbons. The first carbon here has 2 attachments, carbon, carbon, hydrogen, hydrogen. This carbon also here has attachments such as CCHH. This carbon here, for example, has attachments C, 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 C. So, that is a carbon that is attached to all 4 carbons. So, in the first try, when we look at CCCC versus CCHH, this one clearly wins. So, this one will get the first priority. Now to determine the priority order between the second and the third carbon. Now let us look at it again. Now we have CCHH. If you are ever stuck at a point wherein the attachments look exactly the same, what you do is you proceed forward. So you can kind of imagine like you are walking on the road. At any point, if you come to a point where you see all the 4 attachments are same, what you do is you further walk along one of the attachments and see if you find the point of difference. Okay. So herein what I have is this particular carbon versus this carbon. If I look at the attachments here, this particular carbon here has the attachments oxygen, it is again attached to an oxygen. So, OOCC. So, whenever there is a double bond, you write that bond twice, because it is making 2 bonds with that, right. So, it is this particular carbon has attachments of O, O, C and C, whereas in the other case you have the attachments of C, C, C and H. Now, between oxygen and carbon, oxygen wins. So, this one will get a second priority, this one will get a third priority. So, likewise this will be 2, this will be 3. Now, what is our next rule? We have to orient the molecule such that the least priority group goes away from us, and in this case you have the hydrogen going away from you indeed. So, in this case the molecule is showing you an R orientation. So, this is in fact R carbon. So, that is right, and whereas its mirror image which is present in the caraway seed oil is S enantiomer. So, in fact you must have smelled these 2 molecules. One of them is the spearmint, which is a very minty smell, whereas the other one is caraway seed oil. Now, caraway seed oil in Indian context we call it as the saunf, right, and you will remember that these 2 actually smell very differently. Now, one question to ask is if they are really very similar to each other, the same molecular formula, why do they smell differently? Is because your nose has receptors that bind particularly to the one and not to the other, and in the case of caraway seed oil you have different receptors binding. So, what happens is our receptors are chiral, so we smell differently. Okay. So, now let us look at a couple of other examples, and as I said I am going to show a couple of tricks to get to the answer very quickly while naming R and S. Herein let us draw one molecule. I have this particular molecule here. Now, this is 2-butanol. Okay. So, what we are going to do is we are going to label it such that it is R or S. Now, it is very easy to figure out the priority order in this case. Oxygen gets the first one, then this CH2 CH3 group will get the second one, and then this group will get the third one, and the fourth hydrogen, as you can see, is coming towards you. Now, whenever you have a molecule in which the least priority group is coming towards you, of course, you can try to imagine it from the other side such that you can think that the hydrogen is going away, how would the molecule appear to me, and then try to figure out the answer. But one of the quick ways to come up with the answer is you solve the problem imagining that the hydrogen is going away from you. So, in this case this looks like R, right, but in fact I have violated one of the rules and the hydrogen is coming towards me. So, it is not R and it is S. So, whenever I see a least priority group coming towards me, what I think is this looks like R, but it is S, or vice versa. If you get an answer of S, then the real stereo center is really R. Okay. So, whenever the least priority group is coming towards you, just switch the answer, that is what the trick is. Now, let us go to the next one. Now, let us look at the scenario when the least priority group is in the plane of the paper. This is going to be a little tricky, because when it is in the plane of the paper, it becomes difficult to imagine such that the least priority group goes away from you. right. So, now I am going to draw a molecule here, right. So, this is 2-bromobutane. Now, let us try to figure out whether this is R or S. As you can see, the hydrogen is in the plane of the paper. Now, again what you do is you prioritize. So, this is 1, bromine gets the first priority, the ethyl group gets the second, the methyl group gets the third. So, we are good to that part. Now, in order to get the hydrogen such that it goes away from me, what I am going to do is I am going to swap any 2 groups twice. Okay. So, this is important, swap any 2 groups twice. Okay. I am going to first swap. So, in my first swap, I am going to swap hydrogen and methyl such that the hydrogen goes away, which is what I really want. So, that is my first swap, and now that the hydrogen is away from me, I can figure out the configuration, but remember we have to swap twice. So, right now if I get the answer will be wrong. So, what I am going to do is I am going to swap it again such that I am going to, let us say, swap between bromine and methyl. So, that is my second swap. So, what do I find? I will make methyl come here and hydrogen going away from you, CH2 CH3 and then bromine. Now, solve this particular molecule using our regular rules. So, 1, 2, 3, it moves like S and this is S. So, since the stereo center after 2 swaps is S, the stereo center in the original one has to be S. Okay. So, as you can imagine, whenever you have the least priority group in the plane of the paper, the trick is to swap any 2 groups twice. It would be great if you can get the least priority group going away from you, so that you can easily solve that question. Okay. So, there are many chiral molecules in nature, and one of the reasons chirality is so important to us is that most of the natural products or derivatized drugs or medicines are chiral in nature, and when we take them as medicines, most of the receptors in our body, drug receptors, enzyme receptor binding sites, are all chiral in nature. So, chirality is very important study in order to come up with safer drugs or safer medicines for that matter. Now, here I have some of the examples of the chiral molecules that we find in nature. One of them is actually something called as darvone. So, this is one of the drugs that is used as a painkiller, okay, and in fact, its mirror image called as Novrad. So, darvone's mirror image is Novrad, is actually used as an anti-cough agent. So, 2 different enantiomers are used as medicines, but in a different way, right. So, or you can really see here I have plus limonene, right. So, if you really see this particular carbon here is the chiral carbon, right, and this carbon gives rise to the chirality in limonene, and limonene is really present either in oranges or in lemons. And the reason why you smell these 2 things different is that because each of these have a different enantiomer present in them in majority. Here is one more example. So, all of us must have taken ibuprofen as a pain reliever or for fever sometimes in our lives, and unless you are really allergic to ibuprofen. But if you really look at the molecule of ibuprofen, what you will see is that it has a chiral center again, and only one of them is actually active, in the sense only one of them will really act as a medicine for the pain relief. So, the dexibuprofen is actually the pain reliever or really the active molecule, whereas if you look at its enantiomer, this one here, it is not really active and it is going to really not do anything. Okay. So, when drug companies have to sell their drugs into the market, they first have to go through thorough checks, And in the case of ibuprofen, what happens is that it is sold as a mixture of two enantiomers. One of them is active, the other one simply does not do anything to or does not cause any harmful effects. In the case of thalidomide, if you remember, thalidomide was not safe because the other enantiomers caused adverse effects. In the case of ibuprofen, the other enantiomer does not really do much. In fact, our body has an enzyme that converts this ibuprofen, the inactive form, to the active form. So, we do have racemases which racemize the ibuprofen in order to convert the inactive to the active form. Herein I have some more common medicines with the chiral centers. Try to look at all the drugs that are there in the market, try to look at where the chiral center is and name them as R or S. So, for example, you can very well take this slide and try to figure out whether each of the centers in each of these drug molecules is R or S, try to name them. So, naproxen here is used to reduce swelling or is used as a pain reliever. Panthenol is actually provitamin B5. So, you must have heard the ads for provitamin B5 and that is really going to act as the provitamin drug. Then you also have the escitalopram. This one here is used to treat anxiety or depression. Fourth one here, simvastatin, is actually used to treat the patients with heart diseases. So, as you can see, most of the drug molecules in the market today are chiral in nature. In fact, I am going to say some of the other names that you must have heard which are really chiral in nature. So, cholesterol, cocaine, morphine, then you have sucrose, glucose, most of the sugars, most of the amino acids are all chiral in nature, progesterone, estrogen, all of these molecules are going to have some one or the other chiral center in their structure. And that is why the study of chirality or the study of the properties of molecules to orient their attachments differently in a 3D space is so important. So, now let us think about the properties of these enantiomers. So, we have looked at a set of molecules that are mirror images of each other, that are non-superimposable, but what are their properties? One of the key point to note here is that they are pretty much the same except their arrangement in 3D space. So, enantiomers have the same physical properties. So, they have the same melting point, the same boiling point, solubility, refractive index, pretty much all other properties that you can think about, the properties are going to be very similar. All the physical properties are going to be very similar for the two enantiomers. In fact, they are quite the same. However, the enantiomers differ in only one property, and that is the degree to which they rotate the plane polarized light. Okay. So, I am going to write here that pretty much all physical properties are same except the rotation of plane polarized light. Okay. If I take a pure R enantiomer of a compound, that will rotate this particular plane polarized light in one direction, whereas the pure S enantiomer of the same compound will rotate the plane polarized light to the other direction. And if I really take a mixture of these two, then kind of or rather an equal mixture, then I will not see any rotation of the plane polarized light. The instrument which helps me really determine this rotation is called as a polarimeter. So, now let us look at polarimeter, and what polarimeter does is this particular diagram. So, there is a light source, and as you know that light travels in all directions. So, light waves are going to oscillate in all directions and you have the normal light, and then you have something called as a polarizer. So, this polarizer is going to give you the light waves that are oscillating in only one direction. So, it polarizes light and you only have the light waves going in one direction. Now, these light waves, what it does is they pass these light waves that are going in one single plane through the sample, and as these light waves pass through the sample, what is going to happen? The sample, because the molecules have some kind of handedness, the sample then rotates this plane polarized light such that it either rotates it towards one direction or the other. Okay. So, the polarized light will then rotate after it passes through the sample chamber, and the analyzer will then detect whether the light has rotated counterclockwise or clockwise, such that you have a detector. Now, using this instrument, what we can really figure out for any pure enantiomer is its specific rotation. So, what we are going to now see is what is specific rotation. So, specific rotation alpha at a particular wavelength and at a particular temperature is equal to observed rotation over length of the sample cell into the concentration in grams of the substance in 1 ml of the solution. So, this is my concentration. So, let us say that I have a sample. What is the concentration of the sample? L is the path length. So, the path length traversed by the light such that before it comes out of the sample, and alpha here is the angle of rotation that I measure in degrees, and whereas alpha at a particular wavelength or the specific rotation is going to be thus given by alpha divided by LC. So, polarimetry is an important technique in fine chemicals or pharmaceutical industries to assess the identity and purity or the quality of the compound. So, let us say that I want to market a particular medicine, a particular drug molecule. I would have to prove that it is very pure, such that the impurities cannot lead to any side effects. Now, in order to show the purity, one of the ways to do it is of course the purity of the molecule itself, but we also have to prove that the molecule is not existing as a pair of enantiomers, and whether I have a pure enantiomer, you have to test it using polarimetry and show to it that the plane polarized light is only rotated in a single direction. So, polarimetry is specifically used for the measurement of optical rotation of chiral compounds, which can be used to distinguish the identity of two enantiomers. Whether I have R or S can be determined using polarimetry, but remember polarimetry is just telling me is that whether the light is getting rotated towards the right hand side. So, it is also called as dextrorotatory, or L, which is the levorotatory. So, when I take a sample, put it in the polarimeter, all I get to know is whether it is dextrorotatory or levorotatory. I want to mention that this has nothing to do with R or S. Okay. D or L notation do not correlate with R or S, meaning D does not mean R and L does not mean S. Okay. I can have a compound wherein the R enantiomer rotates the plane polarized light towards the right, whereas for some other compound I can have the S enantiomer rotates the light towards the right hand side. So, please do not correlate these two. Okay. What is true is that if I have a particular enantiomer and if it rotates the plane of plane polarized light towards one direction, then its counterpart which is the other enantiomer will rotate the plane polarized light towards the other direction. And that is all. So, I do not get to know whether the molecule is R or S using a polarimeter, I just get to know whether it rotates the plane polarized towards right or left. Then how do people find out what is R and what is S? So, given a molecule, how do we come to know whether the particular compound exists as R or S? The technique used for that is actually crystallography. So, you have to make a crystal structure of the particular compound, subject it to the crystallographic analysis, and crystallographic analysis will tell you whether the molecule is R or S. In fact, if you look at the two enantiomers, here is something I want to point out, is that let us say that the R carbon here rotates the alpha at 20 degrees is minus 62.5, meaning it rotates towards one side. Its counterpart, which is the S enantiomer, will rotate it exactly in the same degree, same number of degrees, just in the other direction. So, this one is negative, whereas this one rotates it in the positive direction. So, now in this chapter we looked at what chirality is, we looked at what enantiomers are, how to name them or how to label them. In the next chapter we are going to dive further into chirality and look at what happens when you have more than one chiral center, for example. So, till then what you can do is you can look around and figure out which objects are chiral, whether they have a plane of symmetry, whether they do not have a plane of symmetry, and what really gives rise to their chirality till that time. Okay.